Hey guys, it's Miss Johnson, and I'm here to bring you our notes for section 11.1. This is part 2. This is the second piece of section 11.1. We've broken that up into 3 pieces, so this is the second piece. We are getting into one sample t-tests for mean, for mu. So when you are completing a one sample t-test for mu, our steps that we are going to go through are the same, which is super awesome. State, plan, do, and conclude. Those 4 things are the same as what we've been doing for 3 other chapters now. So we're going to do the state, we're going to do the plan, we're going to do the do, and the conclude. And when you do state, you state what the hypotheses are that you want to test, and you state the significance level, and then you have to define the parameters. So there's like 3 components to stating it. When you do the planning, you have to identify the method you're using, the test that you're doing, and then you also have to check the 3 conditions, sometimes 2 conditions, usually 3 conditions. In the do, if the conditions are met, which if this is a free response question on the AP exam, they will be. So if the conditions are met, you're going to actually do the calculations. You need to give your sample statistics, you need to calculate the test statistic, and then you need to find the p-value. And then in the conclude section, you're going to make a conclusion about the hypotheses and put it in context of the problem. Okay, so there's a lot of components to all of these questions. That's why they take quite a while and take quite a bit of space, if you will. So we're going to do one together today. So these are our 3 conditions. Just a reminder, you've seen them lots of times now, but we have to state that things were randomly selected or randomly assigned. We also have to state that we've got a large sample. If we don't have a large sample, we have to do the graph and show that there's no skewness or outliers. And we have to state the 10% condition if we're pulling from a larger population. So 3 conditions that we have to identify. And those 3 conditions are these 3 pieces in the big test statistic formula. So to get your t-value, this is your test statistic. It's similar to a z-score. We learned about z-scores way back in chapter 2. It was data minus mean divided by standard deviation, okay? We still have data minus population mean. So sampling statistic mean minus population mean is our numerator. In the denominator, we need the sampling statistic standard deviation divided by the square root of n to allow for sampling variability. So that's where we get our t-value, and then we'll talk about what that t-value does for us. Just remember that there's 3 different sides to this test that you can have. You can have a greater than test where your alternative is that the mu is greater than. You can have a less than test where your alternative is that mu is less than, so then you're on the left side of the tail probability. Or you can have this not equal to 1, which becomes a 2-sided test. That 2-sided test, you need to find your tail probability and double it. Now, depending on your calculator may ask you if you want it to be 2-sided, and then it'll do it for you. But just remember that if you're looking at a 2-sided test, that you need both tails if you're looking at not equal to. We're going to actually do a 2-sided test in our next part. All right, so let's just go through the first question. It says a level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the DO level at 15 randomly chosen locations along a stream. Here are the results in milligram per liter. An average dissolved oxygen level below 5 milligram puts the aquatic life at risk. Do the data provide convincing evidence at the alpha 0.05 significance level that the aquatic life in this stream is at risk? Okay, so that step A right there, it doesn't point blank say to you, perform a significance test, but you have to read it in the question. Do the data provide convincing evidence at the alpha 0.05 significance level, especially if they give you a significance level. Obviously, if they're giving you a significance level, then you need to carry out a significance test, okay? Part B is going to be, given your conclusion to A, what kind of mistake, a type 1 error or type 2 error, could you have made, okay? Explain what this mistake would mean in context. So then we're going to get back to that error discussion. The good news is the type 1 error and the type 2 error are the same. We talked about these when we did significance tests for proportions. Now we're doing significant tests for mean, but the errors stay the same. All right, here we go. So we're going to start with state. In my state step, we want to test. I'm going to test. And then list your hypotheses. Your null hypothesis is that the mu is equal to 5 milligrams per liter. And the alternative is that the mu is less than 5 milligrams per liter. Where, and now name your parameter, mu is the average DO. They've defined DO. Anytime they define an abbreviation for you, you can use that abbreviation. You're allowed to do that. So where mu is the average dissolved oxygen level in milligrams per liter of this stream. And we're going to test it at the alpha equaling 0.05 level. Okay, so there's our state. We have the null and alternative, we have the parameter, and we have the alpha level, those three pieces. All right, let's go to plan. So in plan, this is going to be, this is going to be a one sample t-test for mu. And now let's check our conditions. So random. So we were told that this was a random 15 randomly selected locations. Okay, so that's good. Check. 10%. There are infinitely many spots that you could check this in the stream. Like water is fluid and never ending in this location. So like you could check it anywhere. So 15 is less than 10% of the number of spots you could check DO levels. Okay. Okay, so now let's talk normal large counts. So you probably noticed already that we have a sample size of 15. So n is equal to 15, which is less than or equal to 30. So we check a graph. Now, there's a lot of ways that you can graph this. I'm just going to do a dot plot because there's only 15, so that seems easy enough to me. You could, if you wanted to use your calculator, you could certainly plug this data into your L1, and we're going to end up doing that anyways, but you can plug this data into your L1 and then check a histogram of it if you wanted to see what the histogram looks like. So I need to go from, I see a 3.29 up to I see a 2.87 up to a 5.73. Is that 6.38. Okay, so 2.87 to 6.38. So I've got, we'll say 2.5, 3, 3.5, 4, 4.5, 5, 5.5, 6. That would be like 6.5. Okay. So this is DO level. I did not leave myself a whole lot of space, sorry. In milligrams per liter. And this is 2.5, this is 3, this is 4, that's 5, that's 6. Okay, so let's plot our points. So 4.53 is right about there. 5.04, really close to that 5 line. 3.29, right about there. 5.23, 4.13, 5.50, 4.83. Because these are such, unique decimals. They go out to the hundredths place, so they're kind of unique decimals here. A histogram might almost be a better view just because you can see the range. Like we're obviously not going to have any that cross over. It would be rare that we had any that were the exact same. So we're really just going to get kind of one long line. So a dot plot is going to be good because it's going to show us if we have any outliers or anything, but it's maybe not the best view, but you can kind of see a little bit. 4.66 is right about there. There's that 2.87, 5.73, 5.55. I think I got them all. All right. So here's our dot plot. I don't see any strong skew really. One could maybe argue that these two down here are outliers depending on what your measuring stick is for the outliers. Like if you checked the 1.5 IQR, would they be outliers? I don't know. They don't seem that far away, but there's no strong, definite outliers or skew. So that's what I would say there. The graph shows no strong skew or outliers. Okay, so we test. All right, here's our do. Now we're gonna do. So for do, we gotta carry out the test. We need all of the things. Now, my suggestion to you is to take a second and put all this data into your L1 list. So if you don't remember how to do that, on your calculator, hit your stat button and then go to edit. If you have data in your L1, which I almost always do, go arrow up to that L1 so that it's highlighted at the very top. Hit the clear button. Don't hit delete. If you hit delete, you hit delete the whole L1 list. You don't want to do that. But hit the clear button and then arrow back down and it'll clear that whole list out. So I've done that. Now I'm going to enter my data in. Okay, so I paused for a second and entered my data into my L1 list. Now I'm going to go to stat, calculate, and do one variable statistics of L1. And here's what I get. I get an X bar. This is why I did this, because I need the mean. Now, you could have just added them all up and divided it yourself, but you also need the standard deviation. So it's a lot easier to have your calculator do that for you than to do the standard deviation yourself. So 4.77 milligrams per liter is my mean. My standard deviation is the S of X1, 0.93. It's really 940 if I'm going to round appropriately. 0.940 milligrams per liter. Now, because we're talking about means and not proportions, these things have labels. So just heads up on that. The other thing that's good to know is that your N is equal to 15. I ran out of room at the end of that line. I would have put them all on the same line, but I ran out of room. So then I'm going to calculate my T, my test statistic. So my test statistic looks like the data minus the mean of the null divided by the S sub X over the square root of N. So for us, that's 4.77 minus 5 divided by the 0.940 over the square root of 15. Type all that into your calculator. So I'm going to start in the bottom. I have 0.940 divided by the square root of 15. And then I have 4.77 minus the 5, and I take that negative 0.23 and divide it by the 0.242. And my test statistic looks like this, negative 0.95, roughly. Okay, so there's my test statistic. So now I need to calculate the probability. I'm going to draw you a little picture of what probability I'm calculating. This is where I get my p-value. So in my normal curve, here's my mean of 0. My standard deviation, or my boundary line is this negative 0.95 right here. Okay, the probability that we want is what's underneath that. Okay, so that's the probability that we're looking at. That's the p-value. Okay, so whatever that probability is our p-value. So this is our t distribution of with, I should say, sorry, this is our t-distribution with our degrees of freedom equaling 14. If you forget about that degrees of freedom, the degrees of freedom come from n minus 1. So our n was 15, n minus 1 is 14, so those are our degrees of freedom. So that's what I'm looking at. That's the region there. Now, let's go ahead and find what that p-value actually is going to be. I'm going to use my calculator. So using technology, here's where you can do TCDF. You have a TCDF option in your calculator. So we'll talk about where that is in just a second, but I'm going to write out the things that I need. Lower, I'm going from negative infinity. Upper is to that negative 0.95. And then degrees of freedom, that's the new thing that you need to add into your t-distribution, are 14. So that gives me probability that t is less than or equal to negative 0.95 of 0.1791. There's my p-value. So those are the two things that you absolutely have to have in this do statement. You have to have your t, or your t statistic, your test statistic. That's what that is. Hopefully you can kind of see that green. Sorry, it's a little bright. And then this is your p-value. The other things that are good to take note of are the statistic mean, the statistic standard deviation, and what your sample size is, okay? They're going to want to see formula. If you use technology to get the p-value, you have to identify that, and you got to identify what those values are. Drawing a picture is really helpful, but maybe not necessary, but it is really helpful. It supports your cause quite a bit. But the two things in the box are technically what are part of this do statement. It's just all the other supporting information that gives us those two values. All right, so now let's do our conclusion. So when we conclude, we have a p-value of, I'm just writing this down again because it's on my previous screen. You probably have it right above you. We have a p-value of 0.1791. So our concluding statement says, because p equaling 0.1791 is greater than alpha equaling 0.05, we do not, or we fail, I should say, to reject the null. All of these things that are such little details, like putting in the null hypothesis, including the label of the null hypothesis, like that's, all those things are little nitty-gritty details, but they're going to be really important. Listing your p-value, you listing your alpha level, comparing the two to each other, all of those things are crucial. Let me get rid of those rogue marks so it doesn't look funny on my screen. Okay, so we do not have enough convincing evidence that the stream has a lower DO, and again, you can use the abbreviation because they defined it in the question, level than 5 milligrams per liter. All right, state plan do conclude. Okay, so now we got to talk about B. So in part B, it says, given your conclusion in part A, what kind of mistake, a type 1 error or a type 2 error, could you have made? Explain what this mistake would mean in context. So we failed to reject, okay? Which means we had a high p-value. When you have a high p-value, the type of error that you could have made is a type 2 error. That's how I remember those. Low p-value, type 1, lower error. High p-value, type 2, higher error. So here's let's think about what that means for us. So because we failed to reject, we could have made a type 2 error. Okay, so that's the type of error that we could have made, but then it also says, what does it mean in context? So that's always the kicker. Like, how do we put that into play? So we failed to reject the null, which means that we think the stream is safe. Okay, we think that there's no problems in the stream. The DO level is high enough. It's not too low. If that is an error, if we did that in error, we could walk away from a stream that we think is safe and not do anything to try and help the stream improve, therefore leaving the aquatic life at risk. So that's what our error does to us. So in this case, we may leave the stream alone, thinking it's safe, when in fact it's not. Therefore putting the aquatic life at risk. All right. Okay. A type 1 error in this case, because it's very confusing to think of the two errors. A type 1 error in this case, let's say we found that it was too low. We found we had a low p-value, so we reject the null. And we say, ooh, our stream is in danger. So then what do? Maybe we put some man hours and some time and some money and some treatment into the stream that doesn't, in fact, need it. That would be our type 1 error. If we treated the stream to make the DO level higher, when in fact it didn't need it in the first place, we lose time, we lose money, we lose resources, and maybe even put the aquatic life at risk because we're putting too much in there. I don't know if that's a thing. I don't know anything about the dissolved oxygen level in aquatic life, but that would be a type 1 error. In this case, we found, nope, the stream is safe, everything's great, walk away, let the fish be. And now maybe the stream may not be safe, and maybe we're putting it at risk because we walked away and didn't do anything. So those are the difference in the two errors. They can be very tricky, very confusing. All right, so here's your AP exam tip for the day. It says, remember, if you just give calculated results with no work, and one or more values are wrong, you probably won't get any credit for the do statement. If you opt for the calculator-only method, name the procedure, one sample t-test from you, report the standardized test statistic, t equals negative 0.94. We found 0.95, but that's fine. Degrees of freedom and p-value. There is a way, what this is referring to is there is a way for you to just simply do a t-test. You can go to stat and then over to tests and then do t-test. And then from there, so that's what they're talking about here. If you do this and don't do anything else, some of you may not even have this option on your calculator, but you can see. So then you want t-test. You even have two choices here. You can use the stats, where you'd have a mu of 5 and an x bar of 4.77 and an s of x of 0.94, negative 0.9, or no, sorry, standard deviation of 0.94, n of 15. You don't even need to find the t-value. You don't even need to find the p-value. It's going to do all this for you. Switch your test to less than. I'm looking at my calculator while I'm doing this. So if you're wondering what I'm talking about, it's because I'm on my calculator. And then the t-test gives you once you put all this in, you could either use data and go to L1, or you can use stats and put everything in, x bar, mu, n. And then you get, what it spits out to you is the t-value, negative 0.94. The p-value, 0.1809. They found a t-value that was a little bit different than ours, but that's okay. It was still above. The x-bar, 4.77, that was already stated in the s of x, which is 15. Okay? Or sorry, that's the n. N equals 15. S of x, 0.94. So anyways, if you do this in your calculator, what they are saying is that you have to list these things. You have to put what test you used. You have to put the test statistics. So list all of this stuff out and identify what it is. Don't just put the p-value and walk away. It's not enough. You can't just do that, okay? So that's just their AP exam tip for you for the day. Obviously, you've heard me talk all year about how important it is for you to show your work and list and be explicit about what you are calculating. Okay, that takes us to the end of part 2. So we did a 1 sample t-test for mean. Tomorrow we're going to do a 1 sample t-test for mean, but it's going to be a 2-sided test. So hang tight for that. Thanks for tuning in, and I will catch you next time.